Good morning, precalculus. This is our second lesson in vectors in space. And in this lesson, we'll be learning the dot product between three-dimensional vectors, performing operations on three-dimensional vectors, finding the angle between them, and finding a unit vector. Go ahead and do your warm-up first. You can pause it here. Okay, here are your answers. The dot product for u dot v is -11, and then we use it in the formula when we're trying to find the angle between the two vectors, which is u dot v, or -11, divided by the product of their magnitudes. The magnitude of u is the square root of 58. The magnitude of v is the square root of 5. Use inverse cosine and you get 130 degrees. I always do a quick plot. Here's vector u, here's vector v, based upon their coordinates. And you can see that this angle looks to be 130 degrees. It's definitely greater than a 90 degree. And I just do that to make sure things look correct. All right. Okay, so here are some different operations that we can do with vectors in space, or three-dimensional vectors. Here we have vector v in the ijk components, vector w. And of course we can have a scalar, which is defined as alpha here. So two vectors are equivalent if and only if all their components are the same. You can add two vectors by adding their components. You can subtract two vectors by subtracting their like terms, if you will. And you can scalar multiply a vector by just distributing in the scalar on each component. And of course, finding the magnitude, like I said in the lesson yesterday, the magnitude of a vector in space is just the square root of the sum of all the components squared. So go ahead, pause it here and try to find these different values. And then when you unpause it, you will see the answers. Okay, so as you can see, it's much easier to do addition or subtraction of vectors algebraically when they're three-dimensional. If you were trying to add these, you could do it graphically, but it's really hard on paper to do a 3D plot addition or subtraction, for that matter, graphically. So we just stick with the algebraic method. So here's your answers for plus. Here's your answers for minus. The key is don't forget to distribute the minus on the entire v vector. 3v is just distributing a 3 in here, 9, 15, -6. Here on this one, I would distribute the 2 and then distribute the -3 and then add like terms. And for E, here is your magnitude of W. So I pretty much ignore the signs and just say 2 squared plus 2 squared plus 1 squared and then square root it. All right. Okay, so here's how to find the unit vector. And remember, a unit vector is a vector of length or magnitude 1 in the same direction as any other vector. And this formula is the same one we used for two-dimensional vectors. So it just says the unit vector is the vector divided by its length. So if the vector has a length of 8 and you divide out the 8, you get to a length of 1. And likewise, we can rewrite a vector anytime we want in terms of its magnitude times its unit vector. And this will come in handy later. So let's just do this first example together, and then you can do number 2 on your own. So the first thing I'm going to do is find the magnitude of v, and that is the square root of 4 plus 16 plus 9, which is the square root of 29. So that means the unit vector u in the same direction as v is -2 divided by root 29. And when we simplify that radical, you end up with -2 root 29 over 29i plus 4 root 29 over 29j plus 3 root 29 over 29k. So you want to do it the division by that magnitude on each of the components. All right, in question 2, go ahead and pretty much what you're doing is finding the unit vector for v and then the unit vector for w. So you need to get two different unit vectors. You can pause it here now. And here are your answers. Check your work. Hopefully you were successful. If not, go back and try to find your mistake. All right, so now we're going to find the dot product between two three-dimensional vectors. And just like in 2 dimensions, you multiply your I component coefficients, you multiply your j component coefficients, and then your c, and then you add those together. So I will go ahead and do the example for v dot w, and then you can pause it and try b, c, d, e, and f, and then unpause it to see the answers. So v dot w is going to be 2 times 3 plus 4 times -1 plus -3 times 5. And you end up with 6 minus 4 minus 15, which is -13. Okay, pause it here, try the rest on your own, and then unpause it. Okay, here are your answers. The first thing you should notice is the dot product is commutative. We already knew that. Whether you do v dot w or w dot v, you get the same answers, -13. Then we did v dot itself and get 29. W dot itself, we get 35. And then just so you can see a little property here, I also found the magnitude of v and w, and the magnitude of v is root 29. The magnitude of w is root 35. And note, if you take, I'll just write this out for you. If you take the magnitude of a vector squared, you will end up with the dot product of the vector on itself, because root 35 squared equals 35. Okay, and here we have another formula. This formula is to find the angle between vectors in space. And I certainly hope this looks familiar. It is the same formula we used for 2-dimensional vectors. Once again, the angle between the vectors, no matter where they are in space, is going to be anywhere from 0 to pi or 180 degrees inclusive. It is 0 if the two vectors are identical or going in the same direction and they're parallel, and it's 180 degrees when they're going in opposite directions and it's parallel. But one thing you can do is you can kind of visualize what this angle is if you plot the two vectors. So we're going to do this example here, and the first thing I'm going to do is quickly plot these two vectors. So here's x, y, z. Let's see, I'll plot vector u, do that in red. So we're going to go -2 and then -2 and then up 1. So that vector is here. It's really hard to see. It's going backwards or kind of to the right and then to the left and then up. And then v, I'll do in another color. 3 on the x, 5 on the y. 1, 2, 3, 4, 5. And then down 2. So this vector here is like here. But as you can see, it's really hard to tell, but if, it's definitely going to be less than 180 degrees, but it's kind of somewhere in space. If I kind of connect them, there's your angle between those two. All right, let's go through the work. So the cosine of theta equals their dot product, which the dot product in this case is -18. You get -6 minus 10 minus 2, and then divided by the product of their magnitude. So this is 4 plus 4 plus 4 plus 1 square rooted is 3. And the magnitude of v is going to be the square root of 9 plus 25 plus 4, which is the square root of 38. So when we use inverse cosine, we're going to end up with 166.7 degrees. Now, this is hard to see. I hope you can see that it definitely looks obtuse. You've got the first vector u kind of in red going backwards almost, and then you have the vector v in green almost kind of down and to the right. On the next slide, you're going to be practicing that on your own. Go ahead and try to find the angle between the vectors on your own. Pause it here. All right, now you can see the answer is 105.2 degrees. Note, when you get the cosine of the angle to be negative, you're going to have a second quadrant or obtuse angle. Take a look at the drawing. This hopefully can help you kind of visualize how far apart they are. And that is it for our lesson today. Hopefully that wasn't too much work. Go ahead and give your homework a try.